lecture today is on chaos in 3 dimensions. I'll be talking about 2 different systems. The first will be autonomous chaotic systems. These are not driven like the driven damped pendulum. These are autonomously oscillating systems, and that's the Lorenz and the Rössler. And then we'll be looking at Hamiltonian chaos, which are also autonomous. We're going to start with a discrete map known as the Lozi map, and then talk about the standard Chirikov map, as well as the Henon-Heiles continuous dynamics. In an autonomous 3D chaotic system, one does not have explicit time dependence, and yet one will have at least 3 degrees of freedom, which does enable chaos. So, taking a look at one of the classic models, that's the Lorenz model. So the Lorenz model, it's a 3-dimensional model. So we've got a 3-dimensional flow, so x dot, y dot, z dot, and they're all functions of x, y, and z on the right. These parameters are given kind of standard values that will lead to what's called the Lorenz Butterfly. And so I'm going to go ahead and run this. And so let me bring up the Lorenz Butterfly. So run that as Lorenz. So here's the butterfly here. And so this is the 3-dimensional state space. And I can rotate that around. And so what you see is that, in fact, here's the butterfly, right? So there's the Lorenz Butterfly. So this is a strange attractor. So we can start anywhere for an initial condition. And any initial condition will relax onto this point set. And so this is a point set. It's in 3D, but it has a 0 volume. And so the volume of this Lorenz Butterfly is actually 0. It is a collection of points. I think its fractal dimension is something a little bit above 2 dimensions. And so it has a fractal dimension of about 2.1. And I'll talk a little bit about fractals a little bit later. It does have 3 variables, and so here are the 3 variables in yellow, red, and blue. The 2 variables down here actually are closely related. You can see that, but then they're quite different from the variable, this third variable, which is in yellow. So this is just one of the planes. This is just a projection of the butterfly. I'm not sure whether this is like x, y, but it would be just select 2 of x, y, and z, and then you can project that, and you can project onto the others as well. So the Lorenz Butterfly actually, let's take a look at the parameters. So the Lorenz Butterfly that I just ran has a value of a of 10, b of 50, and c is equal to 8/3. And so going back to this, and so I've got, well, I guess I've got p's, r's, and b's here. I'd have to actually try to map that. But these are the standard values that lead to the butterfly. If I were to change some of these numbers, it'd still be an autonomous system. And it's autonomous in the sense that it just runs. You would pick an initial condition. There'll be a transient as it relaxes onto the butterfly. But then once it's on the butterfly, it will never repeat the same path twice. And in fact, I could even select 2 points that are very close on this butterfly, and I'd let them run in time, and they would diverge exponentially. So just take 2 initial conditions that are close. Let's say they're within epsilon of each other, and then I would let this thing run, and those would diverge exponentially. And that's one of the systems of chaos. It's called sensitivity on initial conditions. The fact that 2 neighboring trajectories will diverge exponentially with a Lyapunov exponent. But if the 2 initial conditions start on the butterfly, then all of the trajectories will remain on the butterfly, but they'll never repeat, and they'll just randomly get as far apart as the size of the butterfly. And so they'll diverge exponentially until they hit the size of the butterfly, and then they'll just stay on that butterfly. So the butterfly really is an attractor, and it attracts all trajectories to it. So it's like an attracting node, only in this case it's an attracting fractal point set. So that's the Lorenz model. I'm not going to spend a lot of time giving the background on that. Some of that you can pick up reading the textbook. Originally it came from atmospheric modeling. It includes things like buoyancy and changes in density with pressure. And it was meant to model some of the real basic convection cells in the atmosphere. And Lorenz was the first guy to do this, and he had access to one of the early computers, and he thought he was going to just be modeling some weather conditions. And next thing you knew, he had really discovered computational chaos. I keep mentioning that Poincaré, about 100 years earlier, had recognized chaos in celestial mechanics, but chaos really came into the modern age with computers and the ability to track these very complex systems, and then recognize that there's a lot of structure in them. Okay, I want to also talk about the Rössler model. The Rössler model is just as classic as the Lorenz. I think it came a little bit later, but it's a little different in the sense that, let's just take a look at this Rössler. You can see that it's almost linear. The only nonlinear term is actually the x multiplying this z term here. And so the other terms here are linear. So it's kind of a minimally nonlinear system. It is autonomous, meaning that I can set an initial condition anywhere in my state space, and the trajectories will run and they'll attract onto the Rössler attractor. So let me just go ahead and run that. Okay. And so here's the Rössler. Now I've set a parameter, a equal to 0.15, and it turns out that the Rössler, when you do that, so the center of the state space is right here. And what you can see is that as the trajectories, this is a projection on the xy, but as the trajectories go around, they do have a well-defined phase. You can define it as the arctangent of y over x. And so this is a chaotic attractor, but this still has a well-defined phase to it. But if I change this up just to 0.3 and let it run, then you can see that now there's actually no well-defined phase because there are these phase jumps and phase discontinuities. Just to give you a sense of the chaos, I mean, so here's, it's a three-dimensional chaotic system, and here are the three variables plotted down here. You can see that the yellow variable is very spiky, and the other variables are kind of trading off against each other. And then this is just another, this is the xz projection, here's the xy projection, so there'd also be a yz projection. I don't think I actually have that here. So this is another classic three-dimensional autonomous chaotic system. There's no explicit time dependence if we go back to the equations. It's just x dot is a function of some function of x, y, and z on the right, so it's a classic flow. And we haven't even had to play that trick of parameterizing time the way we did with the driven pendulum. So these are really the different types of three-dimensional chaotic systems. You've got your non-autonomous driven damped pendulum, and that was one route to chaos. And then here we have the Lorenz and the Rössler model. Okay, well now we're going to move into Hamiltonian chaos. So Hamiltonian chaos is a little different than the dissipative chaos. And so the driven damped pendulum has damping to it. The Lorenz attractor, the Rössler attractor, the reason why they are strange attractors is because there is dissipation that drives trajectories into these transients that relax onto the strange attractor. So what's attracting it, the fact that they're relaxing onto the strange attractor, is caused by dissipation. So the fact that they've got these negatively Lyapunov exponents, and so you approach the strange attractor with a negative Lyapunov exponent, that's coming from dissipation. Now, Hamiltonian chaos is a very different character. It does not have dissipation, and so therefore you do not have strange attractors in Hamiltonian chaos. So an orbit, once you launch an orbit, that orbit will maintain its energy and will visit parts of phase space, and it can do so with great interesting patterns that look random, but there's a lot of structure. And so we'll see Poincaré sections with Hamiltonian chaos that look very reminiscent of the strange attractors. But what they are is just a different beast. That the Poincaré sections will be collections of many, many, many different orbits that are distinct. Whereas with the dissipative chaos, all initial conditions relax onto the strange attractor. And so once you've relaxed, once you're on the strange attractor, the orbits never repeat the same path twice, but they stay on the strange attractor. So with Hamiltonian chaos, we have to pick lots of initial conditions, lots of different initial conditions, in order to probe all the different parts of phase space and Poincaré sections. So with Hamiltonian chaos, we start with our P's and Q's, and so for every Q there's a P, and so phase space and Hamiltonian systems are always even dimensional. And so then here are Hamilton's equations, and so Q sub I dot is equal to the derivative partial of the Hamiltonian with respect to P sub I, and the derivative of P sub I with respect to time is a negative the partial of H with respect to Q. Now if you remember, whether a system will conserve volume depends on the gradient of F. Now F are these functions over here. Okay, so F are the flow functions. So what we're interested in is the relative change in volume as some initial set of initial conditions is evolving over time according to the dynamical equations. And so what we do is we just have to take the gradient of our flow function. And so we'll do that. So d by dx1, that's really d by dq1. D by dx2 is d by dp1 because that's the second variable there. But f in this case is dh dp1, and then this is minus dh dq1. And you get rid of the parentheses because the sequence of the derivative doesn't matter. And I've got the derivative with respect to q1, p1, q1, p1, and so that's 0. This is Liouville's theorem again. So this is the statement that Hamiltonian systems conserve phase space volume as they evolve. Now, it doesn't mean you can't stretch it. I mean, just like you can take taffy and you can stretch it and you can fold it and stretch it again and fold it again. And if you have multicolored taffy, you can mix it. You can get this very complex mixing, but you've never torn it and you've never changed its volume. And so taffy is incompressible, but you can stretch it and fold it. And so you can get very complex orbits with Hamiltonian chaos, but you'll never change the volume of phase space. It just gets stretched, all stretched out. So let's start to take a look at what type of patterns we would get from Hamiltonian chaos. So I'm going to start with area-preserving maps. And this actually goes to one of the last questions in class the other day. Someone asked, well, what happens when your flow K multiplier is equal to 1? In other words, you're on the unit circle. I was a little stumped, but I shouldn't have been because that's classic. When your flow K multiplier is equal to 1, that means that you're in Hamiltonian chaos. It's not an attractor. It's also not diverging. It's neither contracting nor diverging. You're maintaining your volume, and you just keep going and going and going and going. So this is what a area-preserving map looks like. This is called the Lozi map. It's a real simple two-dimensional mapping. So here's xn plus 1 is a function of y sub n on x sub n. Yn plus 1 is a function, in this case, just of the x sub n. We can build our Jacobian matrix of this discrete map and then look at the determinant. So the determinant is telling us whether we're maintaining volumes. And so if we have some parameter b which is different than unity, then in fact if it's less than unity, in fact that would be the flow K multiplier, and it would be a contracting and it would be attracting to possibly either limit cycles or maybe strange attractors might be possible. But in this case, we're actually looking at we want to consider a case when b is equal to 1. And in this case, the determinant is going to be equal to minus 1. And so that's going to be an area-preserving map. And so what I have to do is, because every orbit is different and no orbits attract to each other, and so there are no strange attractors here. So what I've done is I generate a single orbit and I give it a color. Let's say I give it a light blue. All right. And so then this is a discrete map, which is like a Poincaré section. So you can kind of think of this as a trajectory which is coming, some blue point here is from a line that's coming out of the board, and then it circles around somewhere, and then it's coming out of the board again. And what will happen is that this light blue, it's actually coming out of the board here, but then at another cycle it's coming out here, another cycle it's coming out here, then here. You see these light blues. And in fact, these create just a pattern of light blues. And every light blue is actually coming from a single orbit from a single initial condition. Okay, so then let's say, okay, let me pick an initial condition in here that's looks like it's pink. Well, what will happen is I'll actually populate a whole ring of points. So every time I'm coming around in this, circling around in this Poincaré section, it's just going here. I mean, so I'm actually not chaotic at all. I actually have a nice regular motion. And you can tell that I'm close to what's called an elliptical point. And I can be in these other elliptical points, only here they actually will have certain periods. Let's see, so we've got 1, 2, 3, 4, 5, 6, 7. So here's a period 7 orbit. I'm not going to call it an attractor. I have to call it an orbit. So here's a period 7. So these are islands. And I might have an initial condition that goes from here to here to here to here to here to here to here and then back, but never exactly at the same position. But I'll stay on what are essentially tori. These are toruses in a high-dimensional phase space, and then this is just the Poincaré section of that. Now there are regions in which I do get chaos. I mean, so here, out here, these look like just random points out here, and so there's some chaos. Looks like there's a lot of random points around these islands here. There's a lot of random points. Again, remember, a single initial condition leads to a single orbit that keeps piercing the Poincaré plane. And like, for instance, these pink points in here, these are all coming from some initial condition. So this looks like a chaotic orbit. I don't see any islands in there necessarily. And then, but they'll stay here. I mean, they'll actually, these pink points won't show up here. They won't show up here. They won't show up here. So they actually stay in this chaotic region as a single orbit. And so to get all of these different colors meant that I had to pick, I don't remember now, but I think it was something like 500 different initial conditions leading to 500 different colors, each color representing a single orbit in this area-preserving system, where we're assuming that this is a Poincaré section of some higher dimensional conservative flow. All right, so this is called the Lozi map. There's lots of different maps that we could choose from. But there's something called the standard map, and this makes a much more direct connection with Hamiltonian systems, and especially integrable systems. If you remember, if a Hamiltonian is integrable, it means that there are as many constants of the motion as there are degrees of freedom. And in that case, there is always a canonical transformation that'll take you over to the action angle variables. And in the absence of perturbation, if epsilon were 0, I just simply have trajectories which are flat lines. And so I have j as a constant, and it's just going to be a flat line as a function of the action angle. And so I go from minus pi to pi, and so I just have a bunch of trajectories which are flat lines. Now what I'm showing here is what happens if I throw in a perturbation. So now this is due to a non-integrable part of the Hamiltonian. So it means that my underlying Hamiltonian was integrable, and I just had these horizontal trajectories. Now there's a perturbation, and this perturbation just picks this pattern. This is sort of equivalent to having just a rotating system, rotating without gravity, so it's just a system that's rotating. So all these different horizontal lines are just rotations at higher speeds. But then what I do is I give it a periodic kick. So I'm periodically kicking this rotator, and the strength of that kick is given by epsilon. And what will happen is, in this case, for the j, right down the middle, and this does happen. I mean, so it's the action variables that are, let's say, at the 1/2 point, 1/2. That's a ratio of two small integers. And so I'm at the ratio, so j is equal to essentially 1/2 of this full range here. And what will happen when I have this little periodic kick with the small amplitude is I'll actually pick up a saddle point and also elliptical points. And so here are elliptical points, and so I've got these two neighboring flows coming in, and they'll actually get perturbed, and they'll form a saddle point. If you remember, the chaos when we had the pendulum that I was periodically forcing, but I had removed the dissipation. And I had mentioned that it was right around the saddle points, and that's the unstable equilibrium of the pendulum. It was around the saddle point that chaos emerged. And that was actually in the absence of dissipation. And so in fact, when I was looking at that pendulum problem around the saddle point without dissipation, that was actually a Hamiltonian chaos system that I was talking about. So in this case, what's going to happen is we're going to open up the saddle point, and it's at the 1/2 resonance, the 1 to 2 resonance of this system. And that's going to be really important because let's actually do a simulation where we run the map. Let me increase this perturbation up to 0.3. And so what you see is I've actually picked up, I've actually shifted my axis here a little bit. Sorry, I took the upper half and I shifted it, but the hyperbolic point is now actually at the edges, and that's okay. So here's the hyperbolic point right up at the edge here. Here's another hyperbolic point, and then here are elliptical points here at the corners. And so I've gone and iterated this map. Every different color is a different orbit, and every orbit is distinct. And you'll again see that you get these nice tori that open up under this perturbation. And so here's kind of an island chain down here. Some other island chain. Here's an island chain here. Now this is non-chaotic. It's starting to get sort of perturbed behavior. It's no longer an integrable Hamiltonian, but the non-integrability is somewhat small. And so this is non-chaotic. But what I do is I drive that epsilon up to 1. And so now this is chaotic. There still are islands of stability. There still are these elliptical points, and if I start with an initial condition around this elliptical point, they are not chaotic. They will be quasi-periodic. But as I move away from these elliptical points, especially look here, this is where the elliptic point or the hyperbolic point was. Total chaos up there. There's no quasi-periodic behavior at all. There still can be structure. It looks like here's an island here, here's an island, so there's still structure up there. I could zoom in on this if I had sort of higher resolution and had taken this out to more points. So there is structure, so it is chaos. It's not just totally random, but it's not periodic. It's not even quasi-periodic there. What's really interesting is that you'll see that there are these stripes here. Like here's this purple stripe. Turns out that if I look at the golden mean, and I look at it in terms of these resonances here, there's actually a golden mean orbit that is actually a string of islands. It's not chaotic, it's a string of islands. It turns out that the golden mean does show up in Hamiltonian chaos, just as fractals show up in strange attractors. One of the things that shows up in Hamiltonian chaos are things like golden mean orbits, also these resonances, this 1/4 resonance, 1/3 resonance. We'll actually get into this in the next chapter on synchronization. So these resonances, these low ratios of small integer resonances are a big part of what opens up the gaps in the rings of Saturn and things like that. So this is Hamiltonian chaos. It's a discrete map still, so this would still be viewed as a Poincaré section. So let's go to a continuous system. So now this is the Henon-Heiles model. If I have a star in a galaxy, the way the star will kind of move through the galaxy, you view the rest of the galaxy as this background gravitational pattern or structure, and then you've got the single star which is gravitating around this galactic structure. And so then this is a model for that star, of how that star will move. And so you'll see that here's the kinetic energy term in x and y. So this is a two-dimensional x and y model. So I've got a piece of x, a piece of y, and then I've got x and y's. Here are Hamilton's equations, the x dot, y dot, px dot, py dot. And so what we'll do is we'll take a Poincaré section. We'll fix the energy. That'll be a constant of the motion. And then there'll be some piece of x that will be set by initial conditions. And then I'm going to be plotting this on the PYY plane. So this is a 4-dimensional phase space, but I'm going to be looking at a 2-dimensional Poincaré section in that phase space. I just want to show you what that potential looks like. So this is the Henon-Heiles potential. So color is the magnitude of the potential. So what you can see is that there's this is essentially a harmonic oscillator. It's a 2-dimensional harmonic oscillator for very small amplitudes. This just behaves like a harmonic oscillator. But with increasing energy, I get increasing amplitudes, and I probe more and more of what looks like this triangular potential. Here's a big potential hill, here's a hill, but here's a big valley. Now, if my energy of my orbit gets too big, I can actually go over the saddle point, and this is an actual physical saddle point in configuration space. So this isn't a dynamical saddle point, but it's an actual, like a mountain pass, right? So I can actually escape, and then if I get out here, I can go off to infinity. So you can actually get stars that get ejected from galaxies and just go off to infinity. Let's hope our sun never does that. But if you stay low enough energy, you stay in this region here, but this triangular potential makes this chaotic. We get Hamiltonian chaos because it's non-integrable. For small enough energies, though, it is almost integrable. So very small energies will get periodic or quasi-periodic behavior, but as the energy of the system gets bigger, it becomes more and more non-integrable, or it's probing more and more of the non-integrable parts of the potential and becomes more and more chaotic. So first, let me show an energy. This is 0.083, and this is a Poincaré section on P sub y and on x. Here's an actual configuration space. This is in x and y, so this is some initial condition, and this thing has this very directed motion in this triangular potential. And then this is just looking at the speed of the particle or of the star as a function of time. And you get this Poincaré section, which for the moment kind of ignore what looks like chaos that's showing up here. Roughly speaking, if I had a really high precision ODE solver, and if I'd picked my energy just perfectly, and if I'd picked my initial condition perfectly, there'd be a single orbit that goes around like this. And so there's a single orbit that comes around like this, and then it comes around like this, and then through here, and then through here as a single curve. And so it would be a single curve doing this. Actually, I've forgotten where I went. I think it comes this way. And so this is a single orbit. It's a Poincaré section of a single orbit that crosses itself on the Poincaré plane 1, 2, 3 times. So these are hyperbolic points in the Poincaré map. And so at this energy, where I'm just getting a little bit, probing a little bit of the non-integrable part of the potential, what I'm seeing is that I've got these 3 hyperbolic points. And so now if I boost my energy, what's going to happen is I'm going to be probing more and more of the non-integrable part, and so then these are going to start to dissolve into chaos. As you can see, actually, even at 0.08, they already are beginning to dissolve. Here's actually going back down in energy a little bit. This is 0.06. There's this nice regular quasi-periodic motion in this case. This is going up to a much higher energy where I'm now very strongly probing this triangular potential. And then this is chaotic, and then this looks chaotic as well. So let me just run this a few times. Let me actually go in and run Heiles. And so what I'm going to do, so what you're seeing here, I actually forgot what my energy was, but it looks, some of these look chaotic, and so I think my energy was high enough. Some of these patterns look quite regular. That's where I'm going to be around an elliptic point. Others look quite chaotic, and that's when I'm going to be around a hyperbolic point. So you can actually just see it physically in the real configuration space. This is the configuration space here, X and Y. Some of these look nice and regular. Some of these look chaotic. And that is the nature of Hamiltonian chaos, that you can have an initial condition that leads to a very regular quasi-periodic orbit, but then there'll be some other initial condition which just leads to chaos. Okay. And actually, I think I was covering up, yeah, there it is. So here's the Poincaré section coming through. It was covered by my phase space there. And you can see each different color that's showing up is just a different single orbit. So I have to pick lots and lots and lots of different initial conditions in order to populate all these different orbits in the Poincaré section. So this is at an energy of 0.1, and so I'm clearly in chaotic behavior. So if you remember, the hyperbolic points were around here and here and here were the hyperbolic points. So there I have really well-developed chaos around these original hyperbolic points where that curve had crossed itself. But I still get these islands here. So these are elliptic points. And what's also interesting is that there are parts of phase space that I never even visit. So that's pretty much it for today. I just wanted to, here's another view of that Poincaré section for the Henon-Heiles Hamiltonian. This was an actual Poincaré section of a four-dimensional phase space flow. and it just shows the rich nature of Hamiltonian chaos.